the activity series table. Now, when we look at the activity series, note that the activity series shows the reducing agents at the top, and then the oxidizing agents. Sorry, the strongest reducing agents at the top, the weakest reducing agents at the bottom. Okay, so this is just the activity series flipped over. Bruce?
On the that table, there's oxygen in there twice.
Yeah, because note that the other oxygen, the corresponding reducing agent is H2O2. So note that the half reaction or the reduction reaction is different. Okay, let's go on to part B. Due to its unreactiveness, gold is considered a noble metal. Which of the 4 oxidizing agents will oxidize gold? Okay, so let's take a look at table 19.1. And based on what we just said on how to use the table 19.1, which substance oxidizes gold? Now, actually, you can see with cyanide, yeah, so in gold mining, yeah, see, in gold mining, there's 2 things. First, you have to take the gold exists on Earth as gold metal. First thing you have to do is oxidize it to gold ion. Then once you get the gold ion, then you can add cyanide to form this complex ion. I think it's this one. I think it must be. I think this is the complex ion that forms. So this is not, this reaction here is not an oxidation reduction. This is a complex ion formation. This one here is an oxidation reaction. Okay, so there's at least 2 steps in mining. Well, then once you get here, then you have to reverse and get your gold metal back.
What would its state matter be on the way? Would it still be the solid?
Yeah, so this is a solid. This is going to be a solution. For example, an aqueous solution. This is also a solution here too. So we'll call this an aqueous solution. And the reason this is done this way is because it's easier to collect a liquid than it is to collect a solid, especially when the solid is combined with other substances in those minerals. So in other words, this is really a way to separate the gold from the rest of this stuff in the rocks to make gold ion. So then the gold ion is in solution, keeping everything else as a solid. And then once you have this in solution, then it's actually easier to collect this than it is to collect that. Then once you collect this, so you've done your separation and isolation, then you have to reverse and get your gold metal back again. Jeff?
Can you buy cyanide? So if I wanted to go mine some dirt that I knew that there was gold in, could I do that? Or do you need to have a special license?
Well, I'm not sure how easy it is to buy cyanide, although, 20 or 25 years ago, there was this Tylenol poisoning story in the news. Someone had taken some sodium cyanide and added that to Tylenol. And a few people died as a result of that. So maybe it's easy. I'm not sure if it's easy to get sodium cyanide. Now note that gold mining, this is all called strip mining, is not good. Is actually bad for the environment because the cyanide which is produced, or the cyanide which is used, this is very toxic. So this actually binds to the iron in our hemoglobin in our blood, and it actually poisons us the same way as carbon dioxide. So if you have like iron, see iron, the carbon dioxide binds to iron, and the same thing with cyanide. Okay, so those are minus charges. Okay, so that's actually how we get cyanide and carbon dioxide poison. So the use of cyanide in strip mining, I think, is banned in a lot of places because this is very poisonous. Okay, so back to this question. Oh, Jeff, you have an answer to this question?
Oh. No. Where?
Or do you have another question?
But it's different.
So, see, I mean, this is like you say, see, strip mining damages the environment, and this is where a lot of oil companies, because of our thirst for oil, have been accused in third world countries for drilling for oil and then leaving this environmental mess behind them, damaging the environment, causing bad health to the natives in that country. I guess it depends, you know. I guess it depends what your perspective is. Do we want gold or oil? But at what cost?
What about how does asbestos react with the body?
Well, asbestos is also a mineral, so we inhale asbestos, and asbestos is, like I said, a naturally occurring mineral, but somehow I'm not quite sure how it binds to your cell membranes or cell linings, and anyway, it's known to cause cancer, so I'm not quite sure how it does. It's a naturally occurring substance. It's good. It's good for insulation. That's what it was used for.
Well, yeah, they used to go riding in Clear Creek, and then they drowned it because asbestos poisoning.
Asbestos poisoning in where?
Clear Creek? On New Hampshire?
No, but where's the asbestos?
In the ground.
Oh, okay. Yeah, because it's a naturally occurring mineral.
Yeah, I know guys that run there for like 50-something years and they're fine. But you wash your plates in the water, and they have like black stuff all over them.
That may not be from asbestos. Maybe it's something else, not the asbestos.
So the water's clear and you get it out, there's like black stains and streaks.
I'm not sure what the color of this asbestos mineral is, but see, it's this very. I know, you know, if it's a powdery substance, it's easy to inhale. Breathe it in your lungs, and then when it gets your lungs, it's no, black lung is actually a hole, not the asbestos. Okay, so which of these four oxidizing agents will oxidize gold? Okay, so let's see. Let's find gold in this table. So let's see. We know that gold is a reducing agent, so gold goes on the product side here. So where's gold? Let's see.
7th one down.
So gold is 7th one down. So is that in between the where? Where is that in between? The hydrogen peroxide and the what? Or the chlorine? Is it between the H2O2 and the chlorine, the Cl2 and the O2, or the O2 and I2? Okay, so let's see. Gold is right in between the H2O2 and the Cl2, so we put gold here. And this comes from the gold 3+ ion. So based on this table, which oxidizing agent is strong enough to oxidize gold? Yeah, so note that H2O2 would be the oxidizing agent you would use to oxidize gold. Now you may be thinking that, well, what's the big deal about hydrogen peroxide? Because I can buy that in the store. You know, those brown bottles for like, what, $1? 79 cents for a pint or something like that. But see, that solution is only 3 or 5% H2O2, so that's actually pretty effective, that concentration. At higher concentrations, for example, in our stock, we have some 30% H2O2. You have to be really careful with that, because that can actually burn your skin. Yeah, because it's a very strong oxidizing agent. Okay, so it says write a balanced chemical equation to show your answer. Okay, so to do that, we can actually use the table 19.1 to write a balanced chemical equation. So let's do that. So for the H2O2, we have H2O2. Let's see, that was plus 2H plus 2 electrons, and that forms water. Now note that this is a reduction reaction. Okay, so we can do the same thing for gold. So with gold, we have gold 3 plus 3 electrons to form gold. Note that this is also a reduction, but we want to show gold oxidizing. So if we want to show gold oxidizing instead of gold ion being reduced, what we need to do here is to reverse that reaction. So let's write it this way. We have gold going to gold 3 plus 3 electrons. So let's erase this one. Okay, so here's our reduction reaction. Here's our oxidation reaction. And now we can add these together to get our overall reaction. But before we do that, note that in an oxidation reduction reaction, the H2O2, which gains electrons, where does the H2O2 gain electrons from? So if this is gaining 2 electrons, where is it getting its electrons from? From the gold. Okay? In other words, if gold is losing electrons, where is it losing its electrons to? Yeah, to the H2O2. So note that the number of electrons transferred between the gold and the H2O2 must be the same. So there's 2 electrons transferred here, there's 3 electrons transferred here. How do we make them the same?
Times 1 by 3.
Okay, so which one we multiply by 3? Okay, so let's multiply this one by 3. And then we'll multiply this other one by 2. And let's rewrite our equation. So now we have 3 H2O2 plus 6H plus. And then for this one we have 3 golds. Okay, so now we have 3 golds going to 3 gold ions plus 6 electrons. So now let's add this one together and that one together. So now we can get our overall equation. So our overall equation is going to be 3H2O2 plus. Where?
Because you're multiplying that small.
Oh, sorry. 2. Okay. So let's see, we have 3H2O2 plus 6H plus 6 electrons plus 2 golds. And that gives us 6 waters plus 2 golds, ions plus 6 electrons. Are there any substances on each side of the equation which are the same? Yes, let's get rid of these electrons. Are there anything else which are the same? Yeah, so this is our balanced oxidation reduction reaction. Okay. Now, in an oxidation reduction reaction, we have to follow those conservation laws which we discussed in Chem 1A. So for those conservation laws, for an oxidation reduction reaction, okay, so for a balanced oxidation reduction reaction, okay, so it has to follow the conservation of mass law. And there's also this conservation of charge law. Okay, so let's check. Is the conservation of mass law obeyed in this balanced oxidation reduction reaction? Yeah, it says balance. So the conservation charge, sorry, conservation mass is obeyed. Now conservation charge says that the charge on each side of the equation must be the same. So let's see, on the reactant side we have the only charged substance is these 6 protons, so that has a charge of +6. And then we have 2 Au3 plus ions, so 2 times 3 is 6, so note that the conservation charge is obeyed too. Okay, so there's another conservation law. Okay, so note there's a lot of conservation laws. So, you know, for a person on a diet, if they lose 1 pound, that means somewhere else is gaining 1 pound. That's actually conservation math. A lot of